So welcome everyone to lecture 15 of cs267, where we're going to talk about another one of the 13 motifs. And just to remind you which one it is and where it fits into the scheme of things. So here's our picture that we've used before, showing the 13 different motifs that underlie a lot of the different parallel applications of parallel computing that we want to know how to parallelize. And so I've highlighted in blue here structured grids, which appear in high performance computing, but they also appear in lots of other applications as well, and perhaps most notably in image processing, because an image is most naturally expressed as a 2D mesh, and there are also higher dimensional images as well. So the question is, how do we parallelize operations that live naturally on 1D or 2D or higher dimensional meshes? And so the model problem that I'm going to use here to illustrate parallelization techniques that apply much more broadly is going to be the Poisson equation. So we talked about that in the second sources of parallelism lecture, and I'll remind you briefly of what it is. We're not going to worry about the details of the mathematics of why these algorithms converge so much. I'll give you some intuition, but it's going to be used as an illustration of how to parallelize it. So the first method is called Jacobi's method. And at each step, we're just going to be taking all the values on a 2D mesh and averaging with their nearest neighbors, doing the same operation at every mesh point on our structured grid. This is going to be the slowest method, but it's going to be the building block for the later, faster methods. So the next one is a variation on that, red-black SOR. So that's going to be Jacobi on subsets of the mesh with slightly different mathematical coefficients in the algorithm. Then there's conjugate gradients, which is another way to solve problems. And the bottleneck, again, is going to be averaging with nearest neighbors on a mesh, but it's much more general. It applies to a very broad set of systems of linear equations. And finally, we'll get to the optimal algorithm, which is multigrid, which has to operate very differently in order to converge much faster. And so that requires some different techniques. Now, in addition to that, I mentioned this in the sources of parallelism lecture, you can use the fast Fourier transform FFTs also to solve the Poisson equation quite quickly in practice. And that FFTs are so important for many reasons. We'll have a separate lecture on that later, but I just wanted to mention that they're here too. And so just to review some of the notation that we had in the sources lecture. So I want to solve a system of linear equations, which comes from modeling many different things, gravity or image processing or electrostatics, you name it. And I'm going to show you the one-dimensional version of it, which is very, very simple, and the two-dimensional one where I'll spend most of the time. And so I want to solve TU equals F, where T is a simple tridiagonal matrix which is constant along the diagonals. And so you can think of this as an operation on a regular mesh or a structured grid represented by these red dots. And we call it a stencil to indicate that every row is the same, that to multiply a vector by t, you multiply for each value 2 times its value. That corresponds to the 2 to the diagonal, and you subtract its nearest neighbor to the right and the nearest neighbor to the left. And so that is the one-dimensional system that we want to solve, which is you could just do by Gaussian elimination. It's very cheap. It gets interesting when it's higher dimensional. And so here, again, to remind you, is the two-dimensional case. And so now I have a 2D mesh of unknowns. And in this particular case, it's the unknowns are in this 3x3 mesh on the interior. And all the values on these mesh points outside are the boundary conditions, which I need to specify in order to have a unique solution. So I really only have a 9x9 system of equations. And I'm ordering them row-wise, so the first row, the second row, the third row. And the stencil says at each point, you multiply 4 times your own value, and you subtract each of your nearest neighbors. The nearest neighbors to the left and the right correspond to these 2 minus 1s, since I'm going row-wise. And the one above and the one below are these farther away minus 1s. And if this were an n by n grid in the middle, these would be n away from the diagonal. And so 3D will be analogous. And of course, there are many, many other stencils possible too, where people want to do the operations that we're going to talk about parallelizing. this could be, a 9-point stencil. I could include the northeast and the southeast neighbors and so forth. It could have arbitrarily different shapes. All I'm asking really is that it's the same on almost every mesh point. So here is a list of all the algorithms. Again, this is a bit of a review from the second sources of parallelism lecture. All the different algorithms one could potentially use to solve that 2D Poisson equation I had on the last slide, or its three-dimensional counterpart. And just to remind you, they're sorted in two different ways, from slowest to fastest, and from most general, using no special structure about your Poisson equation, down to using all the structure of the Poisson equation, which is exploited by FFT and multigrid. And so if you just pretend it's an N by capital N linear system and use dense Gaussian elimination, it's an N cubed algorithm if you run it in the serial case. We're going to be talking about Jacobi, which gets it down to N squared, and conjugate gradients in red-black SOR, which gets it down to N to the 3/2. And then finally, you get down to the lower bound, which is constant amount of work per unknown. And so that's order N in the sequential case. In the parallel case, I'm going to go into a lot more detail on that, of course, but just to remind you, if you're on this, nice model of parallelism, PRAM, that we use to sort of give you a lower bound. So what's a PRAM? That means you have as many processors as you like and communication is free. Dense Gauss elimination costs you order N. Conjugate gradients in SOR get down to the square root of N, and multigrid gets down to log squared of N, which is reasonably close to the lower bound, which is log N. So let us go on now and talk in more detail just about Jacobi, conjugate gradients, red-black SOR, and multigrid. And I'm looking at the chat. I don't see any questions yet, so I'll just continue.
How can you have order of N memory when there's like N squared variables in 2D?
So, so this number here for Jacobi.
Yeah.
So N, capital N, is the number of unknowns, and we don't need to store the matrix. Remember, the matrix, every row is identical. It's a stencil. And so we just need to remember that we're multiplying, 4 times my value and subtract 1 from the nearest neighbors. All I need is enough memory to store the solution vector. And the solution vector has length capital N.
Okay.
And that's in contrast to dense Gauss elimination, where I, you store the entire N by N matrix, which is, not a good idea if your matrix is a stencil. And in the band case, it goes down to N to the 3/2 because you don't store all the zeros if you're far away from the diagonal. So most of these algorithms just store a few copies of the vector. Does that answer your question?
Yeah.
Okay. So let's derive Jacobi's method. And as I said, all we're going to do at every mesh point, and I'm going to label the mesh points by indices I, j, is we're going to average each mesh point with its nearest neighbors. So the question is, what does that averaging amount to? So what is the equation that we're trying to solve, Poisson's equation, for the ijth mesh point? All I've done here is solve for the uij value. So that's why there's a 4 in the denominator. If I multiplied through by 4, I'd have 4 times this is the diagonal entry. The 4 in the diagonal is the sum of all the nearest neighbors plus the right hand side. So that I have this equation for all different values of I and j. So what I'm going to do now is compute a sequence of approximations. So I'm going to identify which approximation I am at by adding a third index m. So I'll start with my initial guess will be m equals 0, and then I'll compute it for m equals 1 and so forth. I'm not going to keep all of these approximations around, just the last one is all I need. And so all Jacobi does is say, okay, if I know all of these values at the mth iteration, let me just use this equation to get the new value at the m plus first iteration. That means that this equation will be solved perfectly, at iteration m plus 1. Now, the reason I'm not done, of course, is that changing this value of uij means some of the other equations will no longer be satisfied accurately, but it does make progress. So this says, if at the mth iteration, I take this simple weighted sum of all my 4 neighbors, I minus 1j is my neighbor to my left, I plus 1j is my neighbor to my right, and so forth above and below. and there's the right-hand side, and divide by 4. And if you do the mathematics, which we're not going to do here, the number of steps that it takes to converge is proportional to the problem size. And since this is a little n by little n mesh with capital N squared unknowns, and updating all of these, each of these iterations is a constant cost, but I'm doing it for all capital N unknowns. It's capital N times capital N is the serial complexity to do this. So that's the very simplest algorithm that we want to figure out how to optimize. And so let me just give you a hint of why all the algorithms that we're going to be talking about until we get to multigrid, they're all going to be involved just averaging with your nearest neighbors in some sense. And I'm going to give you a little pictorial reason why convergence is going to be sort of slow, and that later we're going to have to do something better than just talk to your nearest neighbors. So I'm going to use a little model problem where I'm trying to solve the Poisson equation where the right-hand side just has a value 1 in the middle and it's 0 everywhere else. So you can think of this as asking the question, if I have a planet in the middle of my mesh, what's the gravitational potential at some distance from the mesh? And it falls off like 1 over the distance. And so not surprisingly, the solution to the Poisson equation is basically 1 over the distance to the middle. And so I get this kind of peak kind of thing. So that's what I'd like to compute. And what is Jacobi going to do? So here, as I said, here's the right-hand side. There's just a planet in the center of the mesh. Here's the true solution. And I'm going to start, let's say, with a solution that is 0 everywhere. And I want to know how fast could I possibly converge? Well, if my initial guess is 0 everywhere, then what happens when I average with my 4 nearest neighbors? If all my 4 nearest neighbors are also 0, I'm going to stay 0. So that is why after 5 steps, the solution is 0 just about everywhere unless you're within a distance 5 from the origin. When you average with your nearest neighbor, information can only move 1 mesh point at a time. And so you're guaranteed to be 0 everywhere when you're 5 away. So, so what's the best we could do if we had some sort of magical algorithm that gave you the best possible solution, but you're still only allowed to average with your nearest neighbors? The best I could hope for is I get the exact solution up to a distance 5 away. And then outside of that, because I'm averaging with nearest neighbors, the solution has to be 0. So my error is at least the height of this cliff. And that's a lower bound on any algorithm on how fast it can converge if all it does is average with the nearest neighbors. So how long does it take for even this point out here to know that there was a planet in the middle? It takes little n mesh points, little n iterations if this is a little n by little n mesh. So that's how many steps it takes just for this processor to have any chance of knowing the right answer. And of course, depending on the method, it may take much longer than that. But so this is an inherent limitation to Jacobi and SOR and conjugate gradient that we'll fix later with multigrid. So let's talk about, so are there any questions about that before I go on to now implementing Jacobi in the best possible way? So at each step, what we're doing is we're taking the average as our 4 nearest neighbors and the right-hand side vector. And so I can express that as doing a matrix vector multiply. And this T matrix is our Poisson matrix. So there's 4s down the diagonal, minus some 4 minus 1s in the off diagonal. And this basically zeroes out the diagonal and divides the off diagonals by 4. And so this averages with the nearest neighbors and adds in a quarter of the right-hand side. So this is just a one-line version of the formula that I had here on this slide. So, if I take all these equations and put them together, all these equations and put them together to go from iteration m to m plus 1, then I get this matrix vector multiply. So how much data do I actually need to keep in memory to implement this? And the answer is I only need 2 copies of the data. I need the mth and I need the m plus first. So then without any worries about race conditions, I can take all the data from this array and update the m plus first array all in parallel. And there's no collisions there. And then once I get this one, I will then use all that information. Then I do a barrier. So I'm done computing U sub m plus 1. And then I go and use the old array to hold U sub m plus 2. And then I just keep ping-ponging back and forth between these two arrays. So I only need to keep 2 copies of the data. So that saves memory a bit. But so let's ask ourselves, what is the cost of doing this? Now, in the sequential case, if the array is too big to hold in memory, or if 2 arrays are too big to hold in fast memory, then it's pretty clear that I'm going to be limited. I'm going to have to copy this whole array into and out of fast memory for every iteration. And so we have a very low computational intensity, right? I read in 1 point on this mesh and its nearest neighbors. I do 5 floating point operations, and that's all the work I do before I have to go on to the next point. And so this is going to, so this obvious sequential implementation is going to be very limited, in time. This is sort of as bad as the BLAS 2. So what about the parallel case? What is our challenge there? Well, here, and we use this idea again in the Sources of Parallelism lecture, we're going to use domain decomposition. So if this is my 2D mesh shown here, and I have 4 processors, I will, in the interest of minimizing communication, it's the same motivation as before, divide up the domain into 4 nearly squares. And that has a nice property that it's load balanced. Every one of these 4 processors will be responsible for about n squared over 4 of the work. And the communication will be minimized, because what do I need to communicate if this mesh point needs to know its 4 neighbors? And that means this blue processor here has to talk to that green one. And so this is, a very similar picture that we did in the sources lecture. So the boundary, every point on the boundary represents a communication. And so what I want to do is choose these shapes, which are squares here, to minimize the surface to volume ratio. And we talked about that before and decided that squares was a very good way to do that. And in this case, each processor is going to update, n squared over p elements. It's nicely load balanced, and it's going to communicate proportional to its boundary, and that is n divided by the square root of p in the 2-dimensional case. So, and that can be a fairly large number, but that is sort of the limit. So the question is, can we do better? These are 2 obvious things we talked about before. And so our goal now in the next optimization is to improve the communication cost of both the sequential and the parallel cases by interleaving multiple updates. So don't think that you have to go all the way, finish all of UM plus 1 before you can go on to U sub m plus 2. We're going to interleave them and get an asymptotic improvement on the communication complexity. But are there any questions about these 2 pictures before I go on to that first interesting optimization? Okay, so I'm going to show this first because it's much easier to visualize in the case of a 1D stencil, a Jacobi on a 1D problem, and then I'll draw the 2D problem later. And so in this case, suppose that I have an array of length 32, which is very small, so I can draw everything. And so each of these black dots represents one of the values of my solution vector x that I'm trying to update at every iteration of Jacobi. The next row of dots right above it represents one iteration of Jacobi, which I've represented as a matrix vector multiply. And just for simplicity, it also involves adding in a constant, but that's okay. And this is another step of Jacobi, and this is another step of Jacobi. And so what I'd like to do is ask, is there some better way to evaluate this than looping over that entire row and computing it, then looping over that entire row and computing it, and then looping over this top row and then computing it? Is there something better that we could do? So I'm going to illustrate this, just for stencil in 1D and just for Jacobi's method right here. But the same idea is going to come up later, and it's going to have a name called the matrix powers kernel. That's what this object is here. We're computing powers of a matrix times a vector, and it can be used to optimize quite a few other methods as well. So the question is, in what order do I evaluate all these little black dots in order to minimize communication, both in the sequential case and in the parallel case? So for that, I have to know what the dependencies are. And since this is just multiplying by a tridiagonal matrix A, roughly speaking, and then adding in a constant, then every entry of this iteration depends on its 3 nearest neighbors, because that's what the stencil is. So it's, minus 2 times my value, 2 times my value, minus 1 times my neighbors. And so implicitly in this graph, I have this dependence. Whenever I want to compute something, I need the 3 values right below it. So what do I need if I'm computing that entry right there? I need the 3 entries right below it. To compute them, I need these, even more entries right below it. And to compute them, I need an even bigger entry right there. So I need a bigger triangle, and that's implicit, in all of these pictures. So let's suppose that, we're in the situation where I can't afford to have all 32 entries in my fast memory, or all 2 rows in my fast memory. So I can only fit a fraction of 2 rows in my fast memory. How do I make progress without, creating too much memory traffic? And so here is a picture to illustrate that. So suppose I can't afford to fit 2 rows, the whole vector x and the whole vector a times x in fast memory, but I can afford to fit about a quarter of each. So these 2 rows fit in fast memory. What can I do based on that dependence graph that I showed you? Well, if I have all of this in memory, then just this bottom row, the first quarter of the entries of x, then I have enough information to compute all of these entries. And because the triangle, the triangle whose peak is right there includes those 3 entries, and I have them all. Then I can compute a little bit less in the third row, and a little bit less in that row. But now this is much, much smaller. And so I can potentially keep all of this in memory at the same time. So I read in this guy, and I update that, I update that, I update that, and there's no more memory traffic. So all of this can be done with 1 read, and I can take not 1 step of Jacobi, but I can take 3 steps of Jacobi. So this is so this is the progress. I'm reading this bit once, and I'm taking multiple steps of the Jacobi algorithm. But of course, I have all of these other black dots that I need to evaluate. So this is called step 1. What do I do next? Well, I'm going to continue processing these things in this same way, where I only need to keep 2 of these partial rows in fast memory at a time. So after I'm done with this blue trapezoid, I'll read in the bottom row of this red parallelogram, read in all those. And then if I keep all of this information from that diagonal and that diagonal, which is a little bit of extra memory, but not too much, then all of the triangles so to compute that, I will need that entry that I've saved, that entry that I've saved in this new value. And I have everything that I need to compute everything in the red parallelogram. And again, I only need to read this row in once, and I can compute all that with no more memory traffic. And when I'm done, I'll just write the answer out to memory. So there's no more memory traffic on the inside, and I can take 3 steps of Jacobi. Then I do the next parallelogram, and then finally I do the last trapezoid at the end here. And so with the same memory, so the point here is that I can now take multiple steps of Jacobi with the same memory traffic that doing a whole row at a time would have taken, just the same memory traffic to do 1 step of Jacobi. So that's an optimization that, as I said, can be applied to many other examples, and not just structured grids. I'm using structured grids here because it's the easiest way to introduce it, but it works on general sparse matrices as well, as we'll see in a future lecture. So that's the sequential optimization. And I'm going to use the same idea for the parallel one. But are there any questions about the sequential one first? Okay. So now it's a very similar picture in the parallel case. But now the idea is the price I'm going to pay here is I'm going to do a little bit of extra redundant arithmetic. But arithmetic is cheap, so I'm willing to do that. So suppose I have 4 processors. Processor 1 is responsible for everything in that rectangle. Processor 2 will be responsible for that. I'll show you that in the next slide. Processor 3 and processor 4. And this is the work they're assigned to do. So what would the traditional algorithm do? It would have to communicate with the nearest neighbors at every step of Jacobi. So at the first step, this processor would have to go to that neighbor and grab that piece of information. So because of that dependency right there, this would be one message to send that message, that value to there. The second iteration would have to have another communication. I'd have to send that piece of information to that processor. And the third step of Jacobi would have another communication with the nearest neighbors. So there's one communication with your nearest neighbors for every step of Jacobi. That was the row by row, or one iteration at a time approach. So what I want to do now is communicate just as much data. I still only want to compute in this, send 3 words, but I want to do it all with one communication. So I want to take 3 steps of Jacobi and only communicate once, not communicate 3 times. And so the trick is very simple. Instead of sending, these 3 numbers represented by those dots, I'm going to send these 3 numbers at the bottom. I'm going to pack these up into one message of size 3, and 3 is how much I would have sent before, and send this all at once from processor 2 to processor 1. Then processor 1 has enough information to compute everything in this blue trapezoid. Now notice that this data here in this little triangle is going to be computed redundantly, both by processor 2 and processor 1, but this is a lower order term, so this is okay. So to repeat, I'm going to take 3 steps of Jacobi with 1 latency cost, with 1 message instead of 3 messages. What is processor 2 going to do? Yes, and so that's what I mean. I'm going to pack all those up and send them. So what is processor 2 going to do? It's going to be very similar. It's going to get 1 message from processor 1 with those 3 words, 1 message from processor 3 with those 3 words, and then it's responsible for everything in this trapezoid. And these triangles on each side are going to be redundant work. Processor 1 will also compute this, processor 3 will also compute that. Processor 3 is similar, and processor 4 is similar. So putting it all together, here is what everybody is responsible for. And I have these overlapping regions to indicate that everything in here in this purple triangle is computed redundantly. It's computed twice, once by processor 1 and once by processor 2, and similarly for these other triangles. But that's okay because, how long is this? This is n divided by p. And we're assuming n divided by p is very large. The size of this triangle here is, p squared or so. And so this should be a lower order term compared to all the work that's done in here. And it's worth doing a lower order term extra arithmetic in order to reduce all of that communication cost, all of that latency. So again, I'm sending 1 message instead of k messages, where k is the number of iterations. So any questions about that optimization, which is different than you would have done if you just took Jacobi as described mathematically and implemented it straightforwardly. So here is the picture in the 2-dimensional case, which is a little bit more complicated, which is why I didn't start by drawing it. So remember, at every step, each processor is assigned a square, a subsquare of mesh points. And so this is the original data, and here are my 3 iterations of Jacobi. To do 1 iteration of Jacobi, I need my nearest neighbors. So these are these little red circles, which are the immediate neighbors of all of these black dots that I own. And then for the next iteration, I'm going to depend on the nearest neighbors again, 1 more out. So I get 2 on each side. And then finally, at the bottom, I have 3 nearest neighbors going out into each processor that I need to communicate from each of these to the one in the middle. So these correspond to the trapezoids that I had in the previous slide. Now it's just in a higher dimension, but it's exactly the same picture. And so at each iteration, I will send all of these red dots to the processor in the middle, and then the processor in the middle can take these 3 steps of Jacobi. And this works in higher dimensions as well. But I won't try to draw those pictures. So there's been an enormous amount of work on optimizing these kinds of stencil operations, and lots of tools exist that people have built, not necessarily for the optimization I just told you about, which is one we developed here, but there are lots of tools that you should use that try to do a very good job of utilizing mapping your stencil operations to all of the low-level details on your platform. And I just want to give you pointers to these. One of the best known is called Halide. That was developed by one of our faculty, Jonathan Rodden-Kelly, in his PhD thesis at MIT. And it's now used in industry quite widely, I think in Google's image processing pipeline. And it's a domain-specific language where you can express your stencil operations at a high level, and it applies lots and lots of low-level optimizations to map it as well as possible to all of your hardware. And so that is something that you should consider using. Here are some of the papers that our group developed over time to take stencil operations and make them run as fast as possible. Again, mapping them as well to the memory as well as possible, the memory hierarchies, using all of the SIMD instructions and so forth, and also doing those optimizations I told you about on the previous slides to avoid communication. CGITS is another project that was done at Berkeley by our colleague Armando Fox et al. And again, this was, you express things in a high level language and use just-in-time specialization to map it down to a specific hardware. And then another older project at MIT called Pochoir, which was done by Charles Lyserson and his team, which is again a domain-specific language where you can express the stencil operations you want to do at a high level, and it tries to map it to hardware. So all of this attention to stencils or structured grids, another word for that, gives you some idea of how important they are, because people have put a lot of effort into optimizing. Let me just give you another little picture of some work going back into history, because this work has been going on for a while. So Mary Hall at Utah has another project funded by the Department of Energy to optimize this on HPC machines. And then Michelle Strout has been working on using polyhedral tiling, which is to ask what are the right shapes. I drew all these parallelograms and trapezoids and so forth, but in general that's a more complicated kind of tiling problem, what the shape should be if you have a more general stencil than simply your three nearest neighbors. But as I said, people have been thinking about this for a while, so let me just go back in history. So Ian Foster worked on a similar problem like this on something called a grid. Now, what's a grid? That is a bunch of computers connected over the internet. It's a little bit old-fashioned language. And so the question was, if your problem is so big, it's spread over different machines over the internet, what is the best way to optimize your computation there? Our colleague Satish Rao and several other colleagues worked on this a while ago, trying to come up with communication lower bounds using a technique called blocking covers, where they said, if we want to optimize this, is there some lower bound on how much you have to communicate in order to do multiple iterations of a stencil operation? And then just to give you an idea of how long people have been thinking about this, this is the oldest paper I know of, going back to 1963. And in this case, the two levels of memory hierarchy that they were talking about optimizing were called core and disk. So a core, this was in the pre-DRAM days. So core was, a little magnetic circle that data was stored on that played the role of DRAM, and disk was your slow memory, and they were trying to minimize that kind of communication. But it was a similar set of algorithms that they were exploring at the time. So stencils have been with us a long time and will continue to be with us for a long time. Are there any questions about that about optimizing Jacobi before I go on to how do you improve mathematically Jacobi and how that changes the optimizations? Okay, so here are two basic improvements that we want to make to Jacobi, which are going to change the convergence, make it converge faster, but they'll also change how we need to parallelize it. And the two improvements are that as we're evaluating the solution and we're updating it, at any point in the computation, some of our nearest neighbors may have been updated more recently than others. Why don't we all, if the recently updated ones are more accurate, we should use them instead of the old values. And I'll show you a picture of what that means. And the other intuition for the improvements says that, well, if I'm going from my mth iteration to my m plus first iteration by adding a correction to it, why don't I add a multiple of that correction? If that correction is a good idea, maybe I should just go a little bit farther in that direction. And so there's a famous algorithm, I'll tell you what it is, and there's an optimal way to say how much farther you should go in the same direction as Jacobi, and it'll give us a big speed up. Okay, so let's do the first improvement first, where we use the most recent values. And so here is the Jacobi iteration that I was telling you about. You take all the values at the mth iteration, compute their weighted sum. I haven't filled in the whole equation, and you use that to compute the m plus first iteration. So what we're going to do now is not use the mth iteration over here. We're going to use the latest one. And the latest one might be the mth, or it might be the m plus first, depending on what order I've done these updates. So let's look at the most obvious way, ordering to do these updates, and ask if we can parallelize it. And this algorithm is called Gauss-Seidel. And so what I'm going to do is, here's my square grid of unknowns, and I'm just going to go in row-wise order, update the first row, update the second row, update the third row. So at any point in time, if I've updated the first I minus 1 rows, and I'm busy updating the ith row, and I get here, what is the latest data that's available to update this? So I have 4 nearest neighbors. The ones above me and to my left, I've updated. I updated that one just a moment ago, but these are not updated yet. So because I haven't gotten there. And so these 2 nested loops say, for each row and then for each entry of the row, I'm going to take the latest value of the one above me and to my left. Those are these 2 m plus 1 values. And I'm going to take the old value of my neighbor to my right and below me. So these 2 values. And so that is a possibly good idea, but it has a problem because we can't parallelize it. It's sort of, if we tried to take this algorithm as it stands, it obviously has to be done sequentially. I mean, I can't update that entry until I've updated that one, because the new value there depends on the new value there. So this is a completely sequential algorithm, which of course, was not an issue when Gauss was busy inventing it. There was a different set of priorities. So, so here I've written down the code again, where I update in left to right order. And so the question is, what order of update would let me have a lot of parallelism? And so here's the trick. Instead of going row-wise, I'm going to divide the nodes into 2 sets based on a chessboard, the black nodes and the red nodes. And so this is node 1, 3, 5, 7 in the first row, and so forth. So the reason so I'm going to think of all the black nodes as one set and the red nodes as another. And the reason this is a good idea is that all the black nodes only have red neighbors, and all the red nodes only have black neighbors. And so if I want to update all of the black points, then I know that all their neighbors are red. And so so the most recent information for the black points will be the old values of all the red neighbors. So for every black point, which is half of them, so lots of parallelism, I will grab the mth iteration from my red neighbors and do the update. Now, once I've finished updating all the red neighbors, all the black points, it's time to do the red points. And so now I know that all my black neighbors have just been updated. And so I can take iteration m plus 1 and use that to update the red points. And so I will ping pong back and forth between updating the red, that's one very large parallel step, and then one big parallel step to update all the black points. And so the question is, this works fine if you have a nice, simple 2D stencil. And because we know how chessboards work, and we only are worried about our nearest neighbors to the left, right, and up and down. What if I have a more complicated graph? Then people have thought about this. It's called the graph coloring problem in theoretical computer science. What you'd like to do is give each node a color, maybe more than 2, so all its neighbors are of a different color. In that case, you can update all the colors in order, and you're guaranteed that all the neighbors have different colors. So when you do them in the same order of colors, you can have perfect parallelism color by color. So one example would be, when are 2 colors enough? And as in the case of a chessboard, that's when the graph is something called bipartite, that you can divide your nodes into 2 sets, and nobody in one set, the black nodes, are connected directly to one another. They're only connected to the other color. So some graphs have that property and some don't. There's a famous theorem you may have heard about, which is, what if in the case of a stencil, for example, I'm only connected, I can draw my dependencies in my graph. So I can imagine a point for each for each square in this chessboard, and which is a vertex in a graph, and I'm only connected to my nearest neighbors. This is a 2D mesh. And the point is, I can draw that 2D mesh quite naturally on a piece of paper without any edges crossing. So, and you can imagine more complicated graphs like that. And there's a famous theorem that was called the four-color theorem that was conjectured in the 1800s. It wasn't proven until 1976 with the computer program, because there were thousands of cases to take into account, that if your graph has the nice property that you can draw it on a piece of paper without any edges crossing, you only need 4 colors. Now, it turns out that the general problem of minimizing the number of colors is NP hard. And so the good news is, so that's bad news. We can't always find the optimal way to do this, but there's an algorithm called maximal independent sets that can be used to come up with a decent approximation. So when we talk about graph partitioning later, you'll hear more about that. So that is one of the iterations. And so how well does red-black Gauss-Seidel work? Well, it converges twice as fast as Jacobi. So a factor of 2 is nice, but there are twice as many parallel steps, because instead of being able to update all the vertices in one step, I have to do all the black nodes and then all the red nodes. So in principle, there's no speed up. So we need one more improvement. And this one looks like this. Remember, at every step, what I'm doing is I'm taking the old value of my approximation of the solution at point ij at iteration m, and I'm adding some correction to it, which comes from some mathematical formula on a previous slide. And so the intuition is that if this is a good correction, if I'm moving in the direction of the solution by adding this correction, let me just move farther in the same direction by adding some constant multiple w to that. So, and this is called successive over-relaxation. So over-relaxing is, that word is there because w is bigger than 1. And it parallelizes just exactly the same way as Jacobi or Gauss-Seidel. And in the case of Poisson, it's well known how to pick the optimal w, and it's just a little bit less than 2. And so I'm not going to do the math here. So, but if you just basically double the correction approximately, then the number of steps to converge goes down by the square root. So instead of taking n squared steps to converge, little n squared, you take little n steps to converge, which drops the serial complexity down to the number of unknowns to the 3 halves instead of the number of unknowns squared. So that is an asymptotic improvement, and is well worth doing, and is also a tool that we're going to exploit inside multigrid and other optimal algorithms. So are there any questions about that before I go on to other algorithms? So I just finished talking about red-black SOR, and it got the complexity of Jacobi down from the number of unknowns squared to the number of unknowns to the 3 halves. And what it required was, doing this other kind of parallelization, which was in red-black order. Okay, so then the next step is conjugate gradients, and it's going to have the same complexity, n to the 3 halves in the sequential case. It's a little bit slower in this idealized PRAM model, just by a factor of log n. And so, but it's much more general in the sense that it applies to very general sets of linear equations. All they have to do is be symmetric and positive definite, and you get very good convergence behavior. So I'm not going to say too much about it. There'll be a later lecture on sparse matrices where it may come up again. So I'm just going to put it here on one slide, and then point out what it takes to parallelize it. So there's a loop which you repeat until the error called rho is small enough. And I don't want to go into the mathematics of why it works. It's basically doing gradient descent on a measure of the residual ax minus b. And so that's why it's called a gradient algorithm. It's just going downhill. And and computes a direction of descent and so forth. So what are the bottlenecks inside the inner loop? Most of the time is spent in this line of code, which is a sparse matrix vector multiply, or the stencil operation, averaging with your nearest neighbors. So again, this is where all the time is spent doing one matrix vector multiply or one averaging with your nearest neighbors, what else happens in the inner loop? Well, there's a dot product, which involves communication, another dot product, and then 3 Saxbys. And if you remember, a Saxby is a BLAS1 operation where I do a scalar times a vector plus a vector. So no communication required and all embarrassingly parallel. The communication is in the stencil operation, the matrix vector multiply, and in the dot products. And as I said, this converges in the same number of steps as successive over relaxation, but it applies much more generally. I'm not assuming very much about this matrix at all. Now, to do this, to take every step is going to require basically a barrier, because I'm going to have to do a couple of dot products and a matrix vector multiply. And depending on your problem size, that can turn into the bottleneck. And so that trick that I showed you about taking many steps at the same, with one communication that I showed you for doing Jacobi can be applied to conjugate gradient as well. And there have been several PhD theses that were written at Berkeley in recent time that, instead of, and it's based on the idea that instead of computing just doing one matrix vector multiply, I do multiple matrix vector multiplies. And then a lot of the mathematics has to change in a complicated way. So I'm not going to show you, but you can take K steps with one communication instead of, for a communication for every step. So that is all I wanted to say about conjugate gradient algorithm before I go on to the next algorithm, which is multigrid. So are there any questions about conjugate gradient before I go on to the optimal algorithm, which is going to be different in a number of ways? Okay, so now we get down to multigrid, and you can see it's going to hit the lower bound in terms of how much work it does. It's going to do a constant amount of work per unknown in the sequential case. In the PRAM case, our idealized process parallel computer, it will take log squared n steps instead of log n steps. So very close to optimal. And so here's the motivation that we talked about before that sort of gave us a reason that Jacobi, SOR, and conjugate gradient could not converge very fast, and what any new algorithm will have to do instead. And so all of these algorithms, Jacobi, SOR, conjugate gradient, basically just averaged with their nearest neighbors. And that meant that information can only move one grid cell per iteration. And so that means that if you have a planet at the center of your grid mesh, then the nodes in the boundary won't know it's there until you've taken, little n over 2 mesh point iterations. And so if I want to converge in a constant amount of time, I can't just talk to my nearest neighbors. I have to communicate to more distant mesh points. So the question is, how do we do that? And so here's a big idea that we're going to use, and it's going to appear multiple times in the semester in order to make things go asymptotically faster. And so the intuition is that if you're very far away from something, the problem somehow looks simpler. And I believe I mentioned this example in the sources lecture in the case of gravity. If you want to approximate the force, the gravitational force on the Earth from the Andromeda galaxy, it's perfectly fine to approximate it by a point mass instead of having a term for each of the little billion stars inside the Andromeda galaxy. And so we're going to do that sort of approximation for Poisson and many other problems as well. So the intuition is that what we're going to do is use those kinds of approximations, point masses or coarse grids in the case of multigrid, to get an approximate solution for the more fine mesh problem that we want to solve, and use that as a starting guess and iterate if necessary. Now, if I take a coarse mesh and if I take a fine mesh and get a coarse approximation to it, I'll show you a picture by just taking every other mesh point, I'll still have a lot of points there. I'll go from n by n to n over 2 by n over 2. That's still a lot of points. And so how do I solve the coarser problem? I'll use the same idea recursively. I'll replace that coarse mesh by an even coarser one. And doing that recursively is going to get the complexity down asymptotically. So I'm going to tell you the details for this today from multigrid, and that'll get the complexity down to order n, constant amount of work per unknown. We're going to see it later in the semester when we do graph partitioning, which is on a very irregular problem. It's used to parallelize sparse matrix vector multiply and other problems. And so there, what we do is we take the graph that we want to partition and we replace it by a coarser graph. And this is the example I used before, which is for grab Milky Way by their center of masses, and do that recursively as well. And so this idea appears multiple times, and any idea that appears 3 times or more should be a standard technique. So that's the motivation. And so let's go on to the details. So here is a cartoon of what a fine mesh solution is that I would like to compute. So this is a potential solution of the Poisson equation on a fine mesh. And so if I take every other mesh point in both directions, I get this coarse mesh. And I think your intuition would agree that this solution here on the coarse mesh is a decent approximation to this one and could be used as a starting guess of this coarse solution for the fine solution. So the problem is, what if my solution looks like this, which is a lot rougher? So what I'd still like to do is use the fact that underneath this, there's something that looks like this coarse mesh, and just do the work on the fine mesh to get these jaggy parts corrected. So this part underlies the basic solution, and I'm just going to do the work on the fine mesh to get these sort of very rapid vibrations from mesh point to mesh point for them to go away. Okay, so to repeat that, I'm going to replace the problem on a fine grid by an approximation of the coarser grid, solve the coarse grid approximately, and use that as a starting guess for the fine grid problem. And then I will update it to get the local solution correct. So if there's jaggy points from mesh point to mesh point, I will do some local corrections only, nearest neighbor only, to get those correct. And so, and as I said, this depends on this coarse grid solution being a decent approximation to the fine grid. So to write down the algorithm, let me just introduce some simple notation. And I'm going to do this in 1D first and then in 2D. And so I'm just going to consider, a 1D Poisson equation. And to make it easy to pick every other mesh point recursively, I'm going to assume I have 2 to the m plus 1 black points, grid points for simplicity. And so it's easy to pick every other mesh point. And so I'm going to call P superscript I, that's the problem of solving the Poisson equation on a 2 to the I plus 1 grid. And I'm going to call that in the linear system. And so now it's 2 to the I plus 1 grid points, but I'm assuming that the ones at the beginning and the end are the boundary conditions. And so the unknowns are only the ones in the middle. And so I only have 2 to the I minus 1 unknowns, plus these 2 boundary points. And the boundary points are going to remain from, whether it's coarse or fine. And so I'm going to call this 2 to the I minus 1 by 2 to the I minus 1 linear system. I'm going to denote it this way. So this subscript indicates the size. And so my fine grid is going to have the largest value, the problem P superscript M. I'm going to replace it by this coarser one, P superscript M minus 1, down to the coarsest problem of all. And so here's a picture. When M equals 3, I have 2 to the 3 plus 1, or 9 mesh points. Those are the black dots there. And only the 7 ones on the inside are the unknowns. To get to the coarse problem, I'm going to take every other mesh point. Those are labeled in red by problem P2. And so now I only have 5 points here. So I've drawn them over here. Problem P2 is to solve this now 3 by 3 set of unknowns, given the boundary values which remain. That's my coarser problem. And then I go one step coarser by taking every other mesh point once again, and I get to the base case where I have 1 unknown and 2 boundary conditions, and I can solve that 1 by 1 system. And that's my base case that I will use in my recursion. So that's the one-dimensional notation. And it's going to be the same notation in the 2-dimensional case, except now problem PI is going to be on a square grid of size 2 to the I plus 1 by 2 to the I plus 1. But everybody on the boundary is a given boundary condition. So the unknowns are just the 2 to the I minus 1 by 2 to the I minus 1 unknowns in the middle. And so here I have a 9 by 9 grid of points and a 7 by 7 grid of unknowns. I take every other mesh point, I get the ones labeled 2. So now I just have a 3 by 3 set of unknowns in this 5 by 5 mesh, take every other mesh point, and I finally get to the base case with one unknown and all of these boundary conditions on the outside. So I will use this notation in order to state the algorithm. Any questions about the notation? Okay. So, so here I'm going to define the notation at a high level, and that will let me write down the algorithm. And then I won't tell you what the, and then I'll do a little bit more detail of what these, pieces mean. So just to remind you, I'm trying to solve problem P superscript I, and P superscript M, that's the finest mesh, and I'm going to go down to the coarsest mesh. And so what I need to do is take a problem that's on a fine mesh, map it to a coarse one, take a solution on a coarse one, map it to a fine one, and then do some actual work that, which is Jacobi-like, to actually improve the solution. So I'm going to have 3 different operators that are going to appear in the algorithm. The first one I'm going to call the restriction operator. That's going to take my fine problem and map it to a coarse one. And so, so this is going to be, a big problem. This one is, a quarter as large. And the simplest thing you could do is simply, sample. That's kind of what I showed you before. I just take the values of my solution at every other mesh point, or it could involve some averaging too. I'll show you the picture, but it's basically a stencil operation with nearest neighbors. So this restriction is going to be some sort of stencil that's going to take my right-hand side, which defines my problem on the fine mesh, and gives me a problem on the coarse mesh. So this is going to be a right-hand side. I'm trying to solve Tx equal B, and this is going to go from a fine problem to a coarse problem. So that's one direction I have to go. I also have to take my coarse approximation and map it to a fine approximation. And so that's called interpolation. So I'm going to take my approximate solution on mesh I-1, that's the coarse mesh, and then basically just do some linear interpolation with nearest neighbors, again, a stencil, to map it to the fine solution. I'll draw a picture there, but both this one in and R are both just stencil operations, and so they're very cheap. Now, I haven't done any useful work yet. I've only showed you how to go from coarse to fine and fine to coarse. Finally, I have to do something, that actually improves the solution. And this is where I'm going to do something like Jacobi or SOR, and I'm going to call it weighted, because even though it's still just a stencil, averaging with your nearest neighbors, the numbers are different. And I'll show you a picture of that later, and as to how it improves. So here I'm going to take my right-hand side, my solution vector, and I will do some averaging with nearest neighbors to get my improved solution. And this all happens at one level on the grid. So that's enough to state the algorithm on one slide. And this is called a multi-grid V-cycle. And the word V-cycle comes from the graph of its call tree, which I'll show you on the next slide. It's just basically recursion from fine to coarse and going back up. So it's a function, multi-grid V-cycle, and it takes in the right-hand side on the finest mesh, BI, and it returns an improved solution, XI, on the finest mesh. It's recursive. The base case is where it's a 1-by-1 mesh. I can solve a 1-by-1 system and return that. Otherwise, I do something more interesting. I'll solve it recursively. I improve the solution just by iterating on my given mesh. And we'll see, I'll draw some pictures, that what we're basically doing is making the solution, the error, smoother. I'm getting rid of the high frequency error. I'll show you a picture. Then I compute the residual. If I had solved the problem exactly, Tx minus B would be 0, but it's not. So I'm going to solve a coarser problem with this residual. And so here's where the interesting stuff happens. I take the residual, I restrict it to a coarser problem. Then I call multigrid recursively to solve that smaller, coarser problem with a starting guess of 0. Then I take that approximate solution and I interpolate it back to the fine mesh. And I get an update, a correction to my solution. And I use that to correct my solution on the fine mesh. Now, if this had solved the system perfectly, the coarser problem perfectly, which it doesn't, then you can just sort of plug this into there and see that my new residual would be 0. So I would have solved Tx minus b equals 0 exactly, but I don't. So I still have to improve the solution again and do a few more iterations of damping the high frequency error. So that at a high level is what the algorithm is doing, and there's the recursive call. But each one of these lines of code is just averaging with your nearest neighbors. It's a stencil operation done in a slightly different way. So here is why it's called a V-cycle. And so this graph shows you both what I is from iteration to iteration over time. So I call the algorithm on the finest mesh that corresponds to, say, I equals 5. It calls itself recursively on the coarse mesh, I equal 4. I equal 4 calls I equal 3 until you get down to the coarsest mesh one by one. And then it starts returning. You use the 1 by 1 mesh to solve the 2 by 2, the 8 by 8, the 16 by 16. And so that's why it's called a V-cycle. So the overall algorithm looks like this. And of course, you might do this multiple times, but this is what we're going to analyze and show that it works very well. And so what is the complexity of doing this? I want to show you why the complexity is perfect of just doing one iteration. So at each point in this V-cycle, all I'm doing is a stencil operation at each point in the mesh. So the amount of work that I'm doing is the number of unknowns at every point in that V-cycle. So each one of these corresponds to the original number of unknowns divided by 4, divided by 16, and so forth. And I'm doing the amount of work proportional to the number of unknowns at every level. So the cost of level I is about 4 to the I, because it's a 2 to the I by 2 to the I mesh. And so the total amount of work is just this geometric sum over all the levels, which is dominated by the finest level. So it's order the number of unknowns. And so that is why one V-cycle does a constant amount of work. And on an ideal parallel machine, if I could do each of these if I had enough parallel processors to do each of these in constant time, then this would take log n steps in order to get all the way down there to the top. And so that's the ideal parallel machine. So the question is, how many of these, how many V-cycles do I need to do to converge? And so here is the beautiful theorem that I'm not going to prove. I'm just going to show you some pictures to give you the intuition. If you do one V-cycle, one called a multigrid, you're guaranteed that the error is going to go down by at least a factor of 2, no matter how many unknowns you have. That means each V-cycle gives you at least one more correct bit in the solution. And so no matter how big your solution is, the number of steps you take depends on how much accuracy you want. It's independent of the size of the finest mesh. And so if you want single precision, which means say 24 bits, then 24 steps, that's an upper bound, will tell you that you'll get full single precision accuracy. And so that is why the complexity is just a constant times the number of unknowns in the sequential case and a constant times log n in the parallel case. And this is the most important property of multigrid, which distinguishes it from all the other methods I talked about, whose number of iterations depends on the problem size, either n to the 1/2 or n. Okay, so let's show you what these stencil operators are and why this multigrid algorithm has these magical properties. But are there any questions about that high-level description before I tell you just a little bit more about why it converges so well? Okay, so let me talk about the solution operator first, which takes your solution on a particular mesh, the problem PI, and just does averaging with your nearest neighbors and improves the solution. So let me do it in the 1D case. So what does Jacobi do? Jacobi just takes 1/2 times your nearest neighbors and also averages it in the right-hand side. The new version we're going to do is just only slightly different. I'm going to take the old value of my old value plus my nearest neighbors and multiply them by 1/3 instead. Now, once I've converged, if the solution were, if these had all converged, you can convince, it's easy algebra to show these two equations are the same. So, but this is going to have a much different convergence property that I'm going to show you a picture of now. But it's the amount of work is almost the same. So I'm just going to show you some convergence plots for a simple problem. And I'm going to show you the original problem and then just 2 steps of convergence. And so here, what I have is the true solution, which is this nice smooth dotted line, sine curve, and the approximation that I'm going to start with, which is this jaggy solid line. So what I want to do is take this jaggy solid line, which it kind of approximates the smooth curve underneath it, and run multigrid, the smoother for a few steps, and see how much the error improves. So that's the first column. The second column is the error. It's the difference between the true solution, the nice smooth sine curve, and the jaggy line. And that's where this jagginess comes from. So you can see that it is, going up and down rather rapidly. And to understand multigrid, I'm going to show you the error in a different coordinate system. I'm going to take the FFT of the error. And this is the FFT of that function that you see right there. And so the horizontal axis is no longer, mesh points, it's frequency. So here's the high frequency error, and there's the low frequency error. And you can see that there's error in the low frequencies and the high frequencies. It's jaggy, it looks, sort of indistinguishable from that. So, and how big is the error? It's about 1.65 is the norm. So let me take one step of the smoother and look at the error again. So here I've plotted it, and you can see that it's still going up and down a lot, but it's much smoother than it was before. So how do I measure the fact that it's much smoother? I take its FFT. And so what you can see now is that the high frequency error, which means the upper half, has gone down significantly, whereas the low frequency error, is still about as big as it was before. In fact, you can show the math says that this has gone down by a factor of at least 3 times smaller than that. So let me do one more step of weighted Jacobi. So now here's the error, and it looks much smoother than before, but it still can be fairly large in some places. And now the high frequency error has gone down a lot. It's gone down by 1/3 squared at least, or 1/9. And so you can see that the solution, the high frequency error is pretty much gone. I've gotten rid of half the error, if you like, and I only have the low frequency error left. And doing any more steps of the smoother won't help very much because it's only going to make this tiny stuff tinier. It doesn't help. So I've gotten the norm down from 1.65 to 0.92. So the question is, how do I exploit the recursion inside the V cycle in order to take advantage of this? So the idea is that you can think of multi-grid as a divide and conquer algorithm in 2 ways. It's divide and conquer by taking every other mesh point recursively, but it's also divide and conquer in the sense that every step gets rid of the upper half of the high frequency error. And so here's a cartoon to show you what I meant. So here, the horizontal axis is the frequency. So this picture here is kind of a cartoon for this picture. And so the horizontal axis is the frequency, and the vertical axis is the magnitude of the error in that frequency. And what the first iteration did, as I said, is going to get rid of the upper half of the high frequency error. So all the error here is going to get multiplied by 1/3 or 1/9 or whatever. So now we go to the coarser mesh. What does that mean? So instead of looking at every mesh point, I only look at every other mesh point. How does that change what corresponds to the high frequency error? Well, high frequency error means that 2 adjacent mesh points can be very different. If I only have every other mesh point, then 2 adjacent mesh points are twice as far apart as they were here. So basically, I can only see half of the frequencies, the lower half of the frequencies that I saw before, because going from point I to I plus 2 is all I can see here, and that's the upper half of the frequencies that I can see there. So when I go to the coarser mesh, I can only get rid of this second half of the frequencies. Then I go to the next coarser mesh, and I can get rid of those frequencies, and so on recursively. So at every step of multigrid, I get rid of half the frequencies that I couldn't get rid of before. And so that gives us this nice convergence property. So Vivek is asking a question. Is the multigrid V cycle generally run once or multiple times? So the actual algorithm does run it multiple times. I'm just trying to give you a picture of one iteration, because this is what we need to understand how to parallelize. And the actual algorithm can be more complicated, something called full multigrid, where I might solve the coarse problem a little bit more accurately before I use it to solve the next coarser, the next finer problem, the next finer problem. And that's called full multigrid. And but I'm not going to, I didn't want to go into those details here because it doesn't affect the parallelization so much. Let's see here. Won't the small high frequency error leftover alias to the coarse grid? So the thing is that this, if the high frequency error corresponds to just two adjacent mesh points being very different, because that's what high frequency error means, then I can't see that in the coarser mesh because I can only see mesh points that are two away. And so I'm not doing the math to explain that too carefully. That's a topic for my Math 221 course, but I'll show you some pictures, about how it really converges so you can see it. Okay, let me show you those pictures. So I did want to show you what the restriction operator looks like. So so the restriction goes from fine to coarse. So the fine mesh, the fine problems I've shown here, it's the dotted line with the little circles, and there's 17 mesh points. And I want to go to the coarse one. And the obvious thing to do is just take every other mesh point, and that gives me the black solid circles. And you can see that is sort of a decent approximation of the fine mesh underneath it. But it actually, you can get a better convergence by letting this point be 1/2 times the fine point where it sits, plus 1/4 times the nearest neighbors. And that's a slightly better approximation. And that's what you use in multigrid in practice. And in 2 dimensions, you have to average with all 8 neighbors, your north, south, east, and west neighbors, and your northeast, northwest, and so forth. And so, but it's easier to draw in 1D. So that's the restriction operator. And the interpolation operator takes something that exists on a coarse mesh. So I only have every other mesh point here at 0.0248. And I need to come up with a fine approximation, and I just do straight line interpolation. So I need the value there, and I just average the nearest neighbors. So that's what the interpolation operator does in 1D. And in 2D, I average with all these 4 nearest neighbors. So let me just show you some convergence plots. And so here is in 1D the true solution. And here's the right-hand side. So the right-hand side is basically 0 everywhere except for a +1, -1, a +0.5, -0.5, +1, -1. And so what I'm going to show you is how fast it converges. And so what here is a plot of the norm of the residual at step m+1 divided by the residual at step m. And you can see it's always less than about 0.2. That means the error is going down by about 0.2 at every step. Nice, fast convergence rate. And I can also see that by plotting the residual on a log scale. And the slope here is basically, the log of 0.2. So here is a more detailed picture of the complete error at every iteration. And so the initial error is this jaggy line. After 1 iteration of multigrid, the error is this dotted line, a dashed line. Then the error is this one, and so forth. And you can see the distance between these error plots is going down by a constant, which is about 0.2. So you can see that's one property of multigrid. The other property is that they're much smoother. It starts out very jaggy, and the error gets much smoother as you go down, because that's what multigrid is doing. It's smoothing out the error. So that's a 1D picture. And here's a 2D picture. And now the convergence, is 0.4 per iteration instead of 0.2. But the theory says it has to be better than 0.5. It's often much better. So let me now finally talk about parallelizing it on a 2D mesh. And so here I have a 32 by 32 mesh, and I'm spreading it out on a grid of 4 by 4 processors. And so what I've done is I labeled each mesh point by which coarse grid they belong to. So I'm starting with at the 5th level. So every point belongs to level 5. So this is P5, and I've just labeled the points here. Problem P superscript 4, I take every other mesh point, and I get the points labeled 4. Problem P3, problem P2, there's only one unknown per processor. And finally, if I go even coarser, some processors are idle. So the interesting thing about multi-grid is that depending on the number of processors and the number of unknowns, you may have idle processors for the very coarsest problems. So let's look at what this pink processor needs to do at every step in order to update itself. When it's working on the finest mesh, it needs to average with its nearest neighbors. And if I'm at this point here, my nearest neighbors are all local, so there's no communication. And no surprise, if I'm on the boundary, I need to get information from my neighbors. So to update that point, I need the points labeled 5 there, and then the ones I own locally. So there's communication for every point, blue point labeled 5. On the coarser mesh, I need all of the points labeled 4. Again, my nearest neighbors, now they have half as many points as before. When I go to the coarse grid 3, again, I talk to all my neighbors, but I have half as many points as before, coarse grid 2. And when I finally get even coarser, some processors are idle because there's no work to be done. So there's some detailed counting. Let me just skip that and go to the final answer, which is what is the complexity of this algorithm? And I'm going to show you, I'm going to count the number of flops, the number of messages, and the number of words moved. And I'm going to compare multigrid, the fast Fourier transform, which is often widely used, and then red-black SOR. And so for multigrid, the number of flops speeds up nearly perfectly. It's going to do, it would do n flops sequentially. It's doing n over p per processor. That's perfect speed up. But because there's some idle processors, when it gets coarse enough, there's also a log p term. The number of messages is log of n, quantity squared. And the number of words sent comes from that usual domain decomposition, the surface to volume thing, and it's n divided by the square root of p. N divided by p, take the square root. FFT, the perfect FFT would be n log n. That speeds up perfectly. But the number of messages behaves quite differently. It depends on the number of processors. So depending on the relative sizes of p and n, either one of these may win. On the other hand, multigrid always wins on the number of words sent. That's the square root for that. And SOR is, loses on all counts. So that is sort of the complexity of all these. And in practice, let me just go to some practice on this now. We don't go all the way down to a one-by-one problem. Typically what people do is they stop long before that, and they'll use a different solver, could use conjugate gradient or a direct method. And so that's one optimization. And another reason it's the course, you don't want to go all the way down to the coarsest grids, is that they're not negligibly cheap. They seem very cheap in a sequential machine, but in a parallel machine, they aren't. Now, and I think the easiest way to look at this is let's look at the 3D problem. And let's suppose that I had a 10 by 10 by 10 mesh assigned to one processor. So that this is a very small problem. And so that processor has 1,000 mesh points. How much? And so it's doing order 1,000 flops, but how much does it have to communicate? How big is the surface area of a 10 by 10 by 10 cube? Well, all the interior is 8 by 8 by 8. It turns out there are 500 points on the surface of that cube. And so the amount of data you have to communicate is about half the total size. And so that tells us that the surface to volume ratio is actually significant in 3D problems. But despite that, people have gotten big speed ups in practice if the mesh is large enough and they don't go all the way down to the coarsest mesh. And so here's some very old data where they got efficiencies of 0.42 and 0.7 for doing multigrid on this old parallel machine with 1,024 processors. People have been parallelizing this for a long time. And there's some active projects at LBL called Chambo and AMREX, where people have been continuing to optimize this. So I will just mention a little bit. So that's the end of multigrid on structured meshes. And since multigrid is a very important algorithm, and it's also used in unstructured meshes, I just wanted to have a little bit of an overview of what changes there. But that's sort of the end of structured meshes. Any questions? So the question is, how does all of this change when you no longer have a nice simple 2D mesh or 3D mesh? And what does it mean to do multigrid anyway? How do you pick every other mesh point? So we need to be able to coarsen the grid, and it's not just a matter of picking every other mesh point anymore. It becomes much more interesting and problem dependent. You can imagine if you had a finite element model, you can have a coarser finite element model, but there are other ways that don't require that much detail. You can just take the original matrix and coarsen it. We still need to figure out how to go from fine to coarse and coarse to fine and back again. So these restriction and interpolation operators need to change. We also need to define the solution matrix. It's no longer a simple formula like Poisson. And so I just want to draw you a few pictures here. Almost done. So I think I showed you this picture in the sources lecture. And so this is actually a structured mesh. It's modeling a tube, but everybody's just connected to their nearest neighbors, and it's a torus. And if I take every other mesh point, it still kind of looks like a torus. But once I get coarse enough, then I have mesh points starting to connect across this border here, and it doesn't look like a tube anymore. So what this means is that when we take every other mesh point, we have to use some geometric knowledge of who's on a surface, who's an interior, and make sure we don't create non-physical connections that weren't there before. And I also showed you this example before, which was a project done by colleagues in the mechanical engineering department, where they were doing finite element modeling of bones of elderly patients to do a more detailed modeling to see if they're at risk for osteoporosis, for loss of bone density, rather than just computing the density. They did a very detailed finite element model of this mesh, and they used multigrid to solve it. And here's what the mesh looked like here. And it was basically a 500 million by 500 million unknowns. And they, to write down the equations for understanding the stress and strain and when this would break. And they solved this system of equations using multigrid on 4,000 processors with 70% efficiency. And they won best prize that year in 2004, the Gordon Bell Prize for the most interesting parallel application. So that's a good place to stop. And that ends our discussion of structured meshes. So happy to take any questions. So there's all of it. So if anybody wants to use multigrid, for their particular problem, then there's a wealth of existing parallel tools to look at.